Hi guys, this is the EdExcel AS level further maths paper from the sample papers, and in this video we'll be taking a look at the further pure mathematics 1 FP1 paper. For question 1, for part A we have to use the substitution t equals tan of x over 2 to show that sec x minus tan x is equivalent to 1 minus t over 1 plus t, where x doesn't equal 2n plus 1 lots of pi over 2 and n is an integer. Well, first of all, I think it would be a good idea to express sine, cosine and tangent in terms of this substitution t. So these are standard results which you should be familiar with. Sine x, that's equal to 2t over 1 plus t squared. Cosine of x, that's equal to 1 minus t squared over 1 plus t squared. And tan x, that's equal to 2t over 1 minus t squared. Okay, these are standard results which you should know. So what we need to do is substitute these into the left hand side for part A. Now sec x, that's the same as 1 over cos, so 1 over this result, we reciprocate this result, so on the left hand side, if we work all this out, we have sec x minus tan x, which is equivalent to 1 plus t squared over 1 minus t squared. Remember, this is the same as sec x. And then we subtract off tan x, so we subtract off 2t over 1 minus t squared. We have this common denominator of 1 minus t squared, and therefore we can combine these fractions together. We have t squared minus 2t plus 1 on the top, and on the bottom we have 1 minus t squared. And if we factorize the top and the bottom, t squared minus 2t plus 1, that's the same as 1 minus t all squared, and on the bottom 1 minus t squared, we can write that as a difference of two squares. We have 1 plus t lots of 1 minus t. Okay, and hopefully you can see that the 1 minus t cancels on the top and the bottom. Indeed, we are left with 1 minus t over 1 plus t, which is the result we wanted to show. Okay, now for part B, we have to use the substitution t equals tan of x over 2 and the answer to part A to prove that 1 minus sine x over 1 plus sine x is equivalent to sec x minus tan x all squared, where x doesn't equal 2n plus 1 lots of pi over 2 and n is an integer. So for part B, again on the left hand side, what we have is 1 minus sine x over 1 plus sine x, and using our substitutions for sine x, that's 2t over 1 plus t squared, we have over here 1 minus 2t over 1 plus t squared, and on the bottom we have 1 plus 2t over 1 plus t squared. Okay, and what we can now do is multiply through by 1 plus t squared. Okay, so we will multiply through by 1 plus t squared, and we will do the same on the bottom as well. Okay, and if we do that, we end up with, on the top, 1 plus t squared minus 2t, and on the bottom we end up with 1 plus t squared plus 2t. Okay, and hopefully you can see that we can factorize this. So on the top we have 1 minus t all squared over 1 plus t all squared, which, happily for us, that's the same as 1 minus t over 1 plus t all squared. And if you look at what we have in part A, 1 minus t over 1 plus t, that's the same as sec x minus tan x. So this thing over here, that's the same as sec x minus tan x all squared. And therefore, because the left hand side is equivalent to the right hand side, the result is therefore true. Question number 2. The value v £100 of a particular stock t hours after the opening of trading on a given day is modelled by the differential equation dv over dt equals v squared minus t over t squared plus tv, where t is in between 0 and 8.5. A trader purchases £300 of the stock 1 hour after the opening of trade. We have to use 2 iterations of the approximation formula dy over dx. For the first iteration is approximately equal to y1 minus y0 over h to estimate to the nearest pound the value of the trader's stock half an hour after it was purchased. Well, there's a couple of things we need to bear in mind. First of all, regarding this statement here, if I just write it down, £300 purchased after 1 hour of opening, that tells us that V0, that's equal to 3. Remember, V is in £100, and T0 is equal to 1. Okay? And we're looking, after 2 iterations, the value of the trader's stock half an hour after it was purchased. Okay, so let's just write this down. Half an hour after it was purchased, we're finding V2, and we know that T2 is equal to 1.5. Okay, and the reason we know that T2 is equal to 1.5, we know that T0 is equal to 1. We're looking at half an hour after this, so T2 is equal to 1.5. And it takes us 2 iterations to go from 1 to 1.5, and therefore our step H, that's equal to 0.25. Okay, and we can rearrange the approximation formula as an iterative formula. Okay, so far, if we write this down in a different color, we have dv over dt naught, that's approximately v1 minus v naught over h. So all I've done over here, because in the question we have v's and t's, I've replaced the y and x with v and t. Okay, and if we rearrange this, we see that v of r plus 1 is approximately v of r plus h lots of dv over dt r, where r is equal to 0, 1, 2, etc. It's a fairly standard thing. Okay, so with that, let's now begin to find the value of v2. Now, first of all, we know that t naught v naught is equal to 1, 3. You can see that here. And therefore, we can find out what dv over dt naught is, and we can use that using this formula over here. So dv over dt naught, that's equal to 3 squared minus 1 over 1 squared plus 1 lots of 3. Okay, and if we work this out, we end up with 2, and therefore we can now work out the value of v1 using this formula over here. So v1, that's approximately equal to v naught plus h lots of dv over dt naught. So what we have over here is v naught, which is 3, plus h, which is 0.25, lots of dv over dt naught, which we just found to be 2. And if we work this out, we get a value of 7 over 2. Okay, so with that, obviously we know that h is equal to 1.25. We can therefore conclude that t1 v1, that's equal to 1.25, and then 7 over 2, that's 3.5. Okay, and now with this, we can find out what dv over dt1 is, again using this formula. So we have dv over dt1, that's equal to 3.5 squared minus 1.25 over 1.25 squared minus 1.25 lots of 3.5. Okay, and if we work this out, we have 3.5 squared minus 1.25 over 1.25 squared minus 1.25 times by 3.5. So we come out with a value of, sorry, this is supposed to be plus. We come out with a value of 176 over 95. Okay? Which, if you want that as a decimal, that's 1.85, etc. Okay? So we can now use this value to find out what V2 is. V2, that's approximately equal to V1 plus H lots of dV over dt 1. So what we have over here is V1, which is 3.5. Okay. Plus H, which is 0.25. Lots of this value over here, the 1.85, etc. And if we work this out, so we multiply this by 0.25 and then we add on 3.5, we come out with 753 over 190. So we have 753 over 190. Okay, and if you work this out, we come out with 3.96, etc. Okay, and if you remember in the question, we were told we have to find what V2 is to the nearest pound, and therefore we can conclude that we have 396 pounds to the nearest pound. Okay. Remember, we have in the question V £100, so we have to multiply this value by 100 first, which if we do that, indeed we do see to the nearest pound we have 396 pounds. Question number 3. We have to use algebra to find the set of values of x for which 1 over x is less than x over x plus 2. Now, there's two different ways you can do this. You can either multiply both sides by x squared and then x plus 2 all squared, or you can take everything over to one side and then combine the fractions. I will do that. So with this, we can take everything over to one side. So we have 1 over x minus x over x plus 2 is less than 0. And if we multiply the 1 by the x plus 2 and the x by x and then the x by the x plus 2 to combine the fractions, we have x plus 2. Let's just get rid of the brackets. We have x plus 2 minus x squared over x lots of x plus 2, and this is less than 0. Okay, and if we multiply through by minus 1, then we have x squared minus x minus 2 over x lots of x plus 2 being greater than 0. Okay, so with that, we can factorize this. On the top we have x plus 1 lots of x minus 2, and on the bottom we have x lots of x plus 2, and all this is greater than 0. And now let's draw a quick sketch to show this. So I've got a quick sketch over here. We've got our asymptotes at x equals -2 and x equals 0, and then we've got the intersection with the x-axis at -1 and 2, and we've got another asymptote at y equals 1. So from this we can see that our critical values, we have -2, which is this asymptote, -1, which is this intersection point, 0, which is the asymptote, and 2, which is the intersection with the x-axis. And we're looking at where the graph is greater than 0. So it's greater than 0 when x is less than -2. It's greater than 0 when x is in between -1 and 0. And it's also greater than 0 when x is greater than 2. So in set notation we have the following as a solution. We have x being less than -2, that's one of them. We have x being in between -1 and 0, that's another solution. And we also have x being greater than 2. Okay, so these here are our solutions. We've got figure 1 over here, which shows a sketch of a solid sculpture made of glass and concrete, and the sculpture is modelled as a parallelepiped. The sculpture is made up of a concrete solid in the shape of a tetrahedron, shown shaded in figure 1, whose vertices are the origin, A with coordinates 2, 0, 0, B with coordinates 3, 0, 3, 1, and C with coordinates 1, 1, 2, where the units are in meters. The rest of the solid parallelepiped is made of glass, which is glued to the concrete tetrahedron. For part A we have to find the surface area of the glued face of the tetrahedron. Now you'd have to identify that the glued face, that corresponds to the triangle ABC. Okay, let's just show this. This over here is where we have the glued face. Okay, that's quite obvious. So let's just write that down. The glued face is ABC. Okay. And with that, we can find out the area of the triangle ABC. And it's quite a straightforward process. First of all, let's add on these coordinates of A, B and C. We've got A with coordinates 2, 0, 0. We've got B with coordinates 0, 3, 1. And we've got C with coordinates 1, 1, 2. Okay. So when we come to find out the area of ABC, we can do this by working out the vectors AB and AC first of all, multiplying those vectors together and then taking the determinant of that and then multiplying that by half. So the area of the triangle, so the area of ABC, that's equal to 1/2 times by the magnitude of AB multiplied by AC. Okay, now AB, that vector is the same as the vector OB minus OA. So we have 0, 3, 1 minus 2, 0, 0. The result of this is -2, 3, 1, which is the same as -2i plus 3j plus k. Okay. Similarly, the vector AC. AC is the same as OC minus OA. So we have OC, which is 1, 1, 2, minus OA, which is 2, 0, 0. The result of this, that would be minus 1, 1, 2. And if we work this out, we end up with minus I plus j plus 2k. Okay? So the area then, that's equal to 1/2 multiplied by the magnitude of minus 2i plus 3j plus k multiplied by minus I plus j plus 2k. And we can work this out on our calculator. So we have 1/2 multiplied by, and if we go to our calculator, we can go to the vectors mode. So go to the vectors mode, define your vector A, that would be 3-dimensional with components minus 2, 3 and 1. And then define another vector with components minus 1, 1, 2. We will now multiply these vectors together. So we want to work out this vector multiplied by this vector. So we have 5, 3, 1. So we have 1/2 lots of the magnitude of the vector 5i plus 3j plus k. Okay? And we can work out the magnitude of this vector. So if we do that, we have 5 squared plus 3 squared plus 1 squared, and then square root that answer, would end up with the square root of 35. So the area is equal to 1/2 times by the square root of 35 meters squared. Okay? Now, for part B, we have to find the volume of glass contained in this parallel pipette. Well, these are common results which you should know. For part B, the volume of a parallel pipette, so let's just write this down. That's equal to the magnitude of OC. So if you go back to the diagram, we have OC multiplied dot product with OB times by OA. Okay, so we have OC dot product with OA times by OB. Okay, and the volume of a tetrahedron, that's equal to 1/6 of OC dot product with OA times by OB. Okay, and if we work this out, we have 1/6 lots of OC. Now OC, the vector OC, that's equal to 1, 1, 2. So we have I plus j plus 2k dot product with the vector OA, which is 2i, multiplied by the vector OB, which is 0, 3, 1, so we have 3j plus k. So we have 3j plus k. So this over here is the volume of the tetrahedron. So if we work this out, we have over here, if we work out first of all, if we go back to defining our vectors, we have OA, which is equal to 2, 0, 0. We have the vector B, which we can now define. The vector B is equal to 0, 3, 1. Okay, so if we multiply those together, so we have vector A multiplied by vector B, we end up with 0, minus 2, 6. So we have 1/6 lots of the magnitude of I plus j plus 2k dot product with minus 2j plus 6k. Okay? So we have 1/6 lots of. Now, if we define these vectors, so we have, if we define vector C to be 1, 1, 2, and if we call the vector D this thing over here, 0, minus 2, 6, we can dot product those together, so we have vector C dot product with vector D, and we end up with 10. So we have 1/6 times by the magnitude of 10, which is 5/3. Okay, so the result of this is 5/3 meters cubed. And therefore, this volume over here, let's just swap those around. So we can now work out this bit over here, which we will do now. So let's just move all of this up a bit. You'll notice that the volume of the tetrahedron is 1/6 lots of the volume of the parallelepiped. So we need to multiply this tetrahedron by 6 to get the volume of the parallelepiped. So we have over here 6 multiplied by 5/3, which is 10. Okay? So we have 10 meters cubed. And therefore the volume of the glass is the difference between these. So the volume of the glass, that's equal to 10 minus 5/3, which is equal to 25/3 meters cubed. Okay, and now for part C, we have to give a reason why the volume of concrete predicted by this model may not be an accurate value for the volume of the concrete that was used to make this sculpture. The measurements may not be accurate. Question number 5. The parabola C has equation y squared equals 16x, and we have to deduce that the point P with coordinates 4p squared and 8p is a general point on C, and we may quote the formula without proof, for the general parabola y squared equals 4ax and dy over dx equals 2a over y. So when we come to do part A, all we have to do is simply substitute in the y coordinate in the left hand side and the x coordinate into the right hand side, and if the left hand side is equal to the right hand side, of course P would lie on C. So for part A, if we consider this point P with coordinates 4p squared and 8p, and if we substitute this into that equation, on the left hand side we have y squared, so we have 8p squared, which is 64p squared, and on the right hand side we have 16 lots of x, so we have 16 lots of 4p squared, which is 64p squared. Of course, the left hand side is equivalent to the right hand side, and therefore P lies on C. Now for part B, the line L is a tangent to C at the point P, and we have to show that an equation for L is Py equals x plus 4p squared. Well, if L is a tangent, well, what we can actually do is, if we compare this 16x, let's change the size of the highlighter. If we compare that 16x with the 4ax, hopefully you can recognize that 4a is equal to 16 and therefore a is equal to 4. Okay, so let's just write that down for part B. We have y squared, which is equal to 16x, and therefore a is equal to 4. Hopefully that's quite easy to recognize. And knowing that a is equal to 4, we can actually find out what dy over dx is by substituting into here. So we have dy over dx, which is equal to 2a over y. So we have 2 lots of 4 over y. We have 8 over y. And we know that what y is, looking at the coordinates of P, that's 8p. So we have 8 over 8p, which is 1 over p. Okay? Now, using y minus y1 equals m lots of x minus x1, we can find the equation for the tangent. Now, for the equation of L, let's just write this down. So the equation of L, we can find out what this is. We have y minus y1, so we have y minus 8p squared equals the gradient, 1 over p, lots of x minus x1, so we have x minus 4p squared. Multiplying through by p, so let's just write this down. Multiplying through by p, we have py, here we have minus 8p. So we have py minus 8p squared equals x minus 4p squared. In conclusion, the line L, we have py equals x plus 4p squared. For part C, the finite region R shown shaded in figure 2, that's over here, is bounded by the line L, the x-axis and the parabola C. The line L intersects the directrix of C at the point B, where the y coordinate of B is 10 over 3, and given that P is greater than 0, we have to show that the area of R is 36. Now, for this question, first of all, knowing the value of A, we can state our focus. Our focus, S, that would have coordinates 4, 0. That's quite straightforward. And our directrix, so our directrix that has equation x equals minus a, so we have x equals minus 4. And therefore, we already know from the question that the line L intersects the directrix of C, so we know that they intersect at the point B, and the y coordinate of B is 10 over 3, and the x coordinate would obviously be x equals minus 4. So therefore, the coordinates of B would be minus 4 and 10 over 3. And now we can find the coordinates of P using B. So with this point, if we substitute this back into our equation L, we can find out what P is, because we know what y is, that's 10 over 3, and we know what x is, that's minus 4. So we have py, so we have p times by y, so we have 10 over 3 times by y equals x, so that's minus 4. Sorry, we have p times by y, so we have 10 over 3p equals minus 4 plus 4p squared, and we wish to find out what p is. And if we multiply through by 3 and then divide by 2, we end up with 6p squared minus 5p minus 6 equals 0, which we can factorize. We have 2p minus 3 lots of 3p plus 2 equals 0, which if we solve, p is equal to 3 over 2 or minus 2/3. Okay? And we know that p must be greater than 0, and therefore p is equal to 3 over 2. And knowing that p is equal to 3 over 2, we can conclude that our equation L, we have 3 over 2y equals x plus 9. Now, with that, we have to find the area of R now. If we find the point at which L intersects the x-axis, we can find the area of the triangle, and then we can find the area under the curve between 0 and p, and then subtract them from each other. So when y is equal to 0, that will tell us where L intersects the x-axis. So when y is equal to 0, we have 0 equals x plus 9, x is equal to minus 9. Okay? So knowing that x is equal to minus 9, we can therefore conclude that, well, let's just add that into the diagram. We have minus 9 over here. So we have minus 9. And what we can now do is find the coordinates of p, because we know what p is in terms of little p, that's 4p squared, and then 8p, and we know what the value of p is, that's 3 over 2. So when p is equal to 3 over 2, the coordinates of p, that would be 4 lots of 3 over 2 squared, and then 8 lots of 3 over 2. So therefore, the coordinates of p would be 9, 12. Let's just add these in to the diagram. So we have minus 9 across 0 up, and here we have 9, 12. Now we can find out the area of the triangle. Hopefully you can recognize that we have a triangle. So the area of the triangle, that will equal 1/2 lots of 9 minus minus 9, lots of the height 12, which is 108. And we know that C has equation y squared equals 16x, and therefore we can rewrite this as y equals 4x to the power of 1/2. And now we can integrate under the curve C to find out the area under C. So the area under C, we can find that out using integration. We integrate between 0 and 9. We wish to integrate 4x to the 1/2 with respect to x. So we have 8 over 3 x to the power of 3 over 2 in between the limits 0 and 9. So if we work this out, we have 8 over 3 times by 9 to the power of 3 over 2 minus 0, which is 72. And therefore the area of R, that will equal 108 minus 72. 108 minus 72, that would be 36. So we have 36 units squared. Okay.